Hello, my name is Liam Taylor, and today I am excited to present this pre-recorded talk about the evolution of deferred reproduction in birds, focused on the intertwining roles of life history evolution, development, and behavior. Imagine a fish. This is a classic toy model for understanding the role of development in the evolution of age at first reproduction. We need 3 facts about our fish. First, there's some chance that it will die in any given year. Second, the bigger the fish is, the more eggs it can produce in a given year. Finally, to keep things simple, our fish stops growing when it begins reproducing. Our fish has to strike a balance. For any year it keeps growing, it will be able to produce more eggs in the future. But as long as it defers reproduction, the more likely it is to die before beginning to reproduce at all. The optimal age at first reproduction will be a balance of these forces. Note that if there is no developmental opportunity, there is no possible selection for deferred reproduction. No matter how unlikely you are to die, it is always better, all else being equal, to begin reproducing as quickly as possible. Here are 3 facts that make a puzzle. First, many lineages of birds defer reproduction for multiple years. We'll explore this in a minute. Second, unlike our imaginary fish, young birds grow quickly to nearly adult size. For some species, this can happen in a matter of days. Third, in a macroevolutionary sense, birds seem to be somatically capable of developing mature gonads at least within a year. So why are young birds not sexually active, even though they are, generally speaking, sexually mature? Why do birds not reproduce, even if young bird bodies might be capable of reproduction? Unlike our fish, the answer isn't body size or somatic growth. Well, I'm presenting at this conference for a reason, and it's because the kinds of development that are left all have to do with behavior. To take a broader view, here's a phylogeny of about 600 bird species constructed from the Yetz bird tree site. I'll give you the quickest tour possible. Here on the right are basically ostriches, ducks, chickens, a bunch of seabirds, and on the top a huge clade of passerine songbirds, including sub-Oscine passerines like flycatchers. Now I've added some color to the tree. The colors mark the age at first reproduction, where orange means waiting longer to reproduce, and purple means reproducing more quickly. You can see, for instance, lots of songbirds at the top that reproduce in their first or second year, while a bunch of seabirds at the bottom, marked in more orange, defer reproduction for longer periods. I got the data for this tree from the Cornell's Birds of the World Encyclopedia, and each taxon has the higher average value across sexes. Now I've used the software Bayou to estimate shifts in the evolution of age at first reproduction. If you're familiar with OU models, these circles mark where a really good model might assign a different optimum peak parameter for a given clade. Essentially, these circles start pointing us towards places where the evolutionary regime governing age at first reproduction might be shifting. As you can see, there are a lot of circles, and rather than trying to exhume some universal single covariate across this whole tree, I think we need to think about the diversity of development and behavior in birds. So using this tree as a guide, we can explore some of the things that birds might get better at. We'll start with a clade of small seabirds that defer reproduction for 3 or more years. For our purposes, one particularly interesting bird is the herring gull. Here's a photo showing a first-year herring gull on the front and an older breeding bird behind. It takes most herring gulls between 3 and 5 years to begin reproducing. So what do herring gulls get better at? It might have been your first guess. They get better at foraging. Here's a figure from 1983 showing foraging speed increases for older herring gulls. Of course, this kind of development is sufficient for the evolution of deferred reproduction. If reproduction and survival both cost calories, and calories cost time, then an increase in foraging efficiency is a decrease in the effective cost of reproduction. Makes sense. We can look back at our tree to get a little more complicated. Here, for instance, is a clade of Albatross. I want to think about the fact that most of this lineage defers reproduction for almost a decade. What do albatross get better at? Wandering albatross are large, long-lived seabirds with biparental care. Reproduction for wandering albatross requires 2 parents to take care of eggs and young across months, as the parents fly thousands of kilometers to get food. For the first 5 or so years of life, young albatross disperse into the open ocean. So this is sounding a bit like our herring gull. Very young albatross need to develop the ability to forage in particularly intense environments. But at the age of 6 or so, young albatross return to their breeding colonies. They return even though many of them won't begin reproducing for 3 or more years. So what are these young birds doing? Apparently, they're developing pair bonds. Here's a figure from 1988 showing wandering albatross engaging in courtship with more and more partners in the years after they return to the breeding colony, but before they begin reproducing. In the final year before they begin reproducing, you can see the number of partners collapse as they more strictly associate with their bonded partner. Like foraging ability, this pair bond is essential for reproductive success. It takes the coordinated effort of two parents to fledge a chick. So now we have a bird with deferred reproduction structured not only by the initial task of foraging development, but also the social task of choosing a mate and developing a pair bond. But we can get even more complicated. Here are long-tailed manakins, this spike of orange nested near the flycatchers. Male long-tailed manakins are part of lek hierarchies that involve between 3 to about a dozen males. At the top of the hierarchy are the alpha and beta males, the two of whom perform a coordinated display for visiting female audiences. By and large, only the alpha male will successfully mate with females. Beta males can spend more than 10 years in their subordinate position before possibly rising to an alpha position. This is why the average age of first reproduction is so high for males of the species. So what are these young males doing? First of all, they're developing the individual skills for cooperative displays. Work from Jill Traynor and Dave McDonald has shown how displays involving older beta males have better coordinated songs. Here's a cartoon of the song notes of two displaying individuals, and we can see how a measure of coordination improves for older partners. This is already pretty wild. What young males are developing is an intersexual display, meaning the evolution of deferred reproduction in the species is structured by the dynamics of female preference itself. But it gets even more intense, because females will continue to visit sites with good performances, even as individual alphas change. Female visitation responds to the cooperation and orderliness of the male hierarchy. So aside from any individual enterprise, another thing that is developing is the social institution of a cooperative display itself. The whole process is social development, although it seems quite a bit different than what we usually call social learning. Think of whale songs or tool use. This isn't a picture of memes transmitting from one individual to another like a virus. The birds constitute the development of the social relation themselves. We are now a full universe away from body size and somatic growth, despite still being comfortably within the confines of the classic predictions of life history theory. That's what I've got today. This is a pre-recorded talk. If I'm not available, please do not hesitate to reach out. Here's my email and my Twitter, and thank you for listening.